This meeting is being recorded.
For problem 14 from chapter 14, we are given 4 scenarios here, and we're asked to describe in each how we could use IR spectroscopy to monitor the progress of these reactions. So we see in A here, we see an alcohol as our reactant, and then we see a different functional group in our product. So we're going to look for what characteristic stretches and the wave numbers of those signals that we should expect. And through our analysis of what wave numbers we generate, we can see whether or not we have a product formed or if we still have our reactant present. So we would expect with our starting material to have an OH stretch for this alcohol, and it would have a broad signal between around 3200 up to 3600. And that's really the main signal that we'll look for in our above our fingerprint region. And then we have over here, we have our carboxylic acid. So again, we expect that OH stretch, but now in a broader range. So anywhere from 2200 up to that 3600 range. And then we also have another signal that would appear, the one for the CO stretch of this carbonyl here. And we expect that to be for a carboxylic acid around 1715. So for this specific case, we could comment that we have this overlapping signal that between our alcohol and our carboxylic acid. So that may not be apparent, but when our product is formed, we will have this additional signal here that's generated. So we could use that specific signal to monitor our progress. Let's take a look at what happened in B here. So our starting material is an unsymmetrical alkyne. So we'll name this. And this unsymmetrical alkyne, we expect to give us a signal around 2200 or so for that CC stretch. And then in our product, we see that we have an sp2 hybridized hydrogen here and here in our alkene. So again, that sp2 carbon hydrogen stretch can be observed, and this would generally be around 1600. And what else do we have here? Oh, I'm sorry. So the unsymmetrical alkene rather would have that stretch around 1600, and then the specific sp2 hybridized carbon CH stretch would appear around 3100 rather. So we're going to have 2 signals in our product here, one at 3100 for the CH stretch, one around 1600 for a CC stretch, and then our alkyne, we saw that we had a signal around 2200. So we will have completely different signals in different ranges. So this progress would be maybe a little easier to monitor than our part A. So let's take a look at what happens in part C here and what signals we would generate. So we have our triple bond here in our starting material. This is a symmetric compound, so we would not see a CC stretch here because there's no net dipole moment in that carbon-carbon triple bond. Also, we see that the CC double bond stretch here would not be apparent, again, due to symmetry within our molecule. But what we would see would be with our alkene product, we would have a signal around 3100 for that this carbon that's sp2 hybridized bonded to that hydrogen. So something like this right here or this right here. This signal would be present in our product and it would not be present in our reactant. So we could look for a signal around 3100 to appear, and that would indicate that our product was formed. And let's take a look at our last scenario here. So our starting material, we should see 2 signals in the double bond region, so the carbonyl and the CC double bond. So collectively, these 2 signals would appear between 1600 and 1850. And in our product, this would only have a signal for our CO, double bond. And that would again be in the same range. So we would look for the appearance, or rather a disappearance of one of those signals to monitor our progress in part D.